Hello and welcome to this new episode of Commodore 64 Games Reverse Engineering. I'm going to be reverse engineering a complete game and providing all of the source code so that you can actually use this source code to then create your other games. I'm going to be looking at the shoot 'em up construction kit. So why create all of this new code? Well, to reduce slowdown and flicker in SEUCK games that we used to see before. Remove the sprite to background scroll stop wobble. This is where the sprites kind of slightly disconnect from the background when scrolling starts or stops. And also remove the wasted memory because there is quite a lot of editor code and graphics still mostly present in the final game. This will allow a lot of extra functionality to be added to games because there's full source code and it can be completely customized, for example, by adding extra player weapons upgrades or super weapons, for example, parallax scrolling, enemy homing bullets where enemies can fire at you. Enemy movement AI can be improved rather than just having a pre-recorded attack wave. The title screen can be improved, and also adding functionality like high score tables would be quite possible because there's full source code. In the previous video we looked at enemy attack waves where they spawn, what type they are and where on the screen, but this time we're going to have a look at the second part, which is enemy movement. I'm going to do the same as I did in the previous video, so starting with blank SEUCK editor and creating a new enemy which basically reuses the player's sprite but makes it white rather than, the light blue colour by default. So this is the game as it is without enemy attack waves. Let's change the level parameters so that the first screen is a still screen rather than scrolling very quickly. This will make it easier to look at the enemy's movement in detail. I want to save that as the base data first of all, so that there's no enemies so far. This is just, there's no attack waves inserted. There's one enemy animation that's being created. If I insert an enemy right down at the beginning of the map, right down at the bottom, and I add the first enemy up in the top left-hand corner of the screen, and immediately I'm going to press F7 to store that enemy. I'm not going to move it anywhere or anything else like that. Just make a note of what the first enemy is and where it is and what it does. So the top left is static, and at the same position in the map, I'm going to add another enemy in the top right. This time, I'm going to move it left, one step. So I basically tapped the joystick left once. And a third enemy, this time in the bottom right-hand corner of the screen. And this time, I'm going to move it up one tap, just one tap. The reason why I'm doing this is that I want to see how very short movements for enemies are encoded, and to see if I can look at this short encoded data and then deduce the data format that's used for the movements. The previous video for the attack waves looked at the position, or start position, the enemy type, so on and so forth. This time I'm moving the enemy to the right once. This is the enemy in the bottom left, and then I'm moving it down once, because right and then down is a two-step process. So I basically want to see how a slightly longer attack wave movement is encoded in the memory. If I do a proper test of this, and now I'm advancing each frame one by one, so I've paused the game, you see, and I'm advancing a frame. So every time I press Alt and plus, it advances one frame. You can see that Vice is paused in the title window title there, and you can see the frame tick up. And as I advance the frames, you can see eventually that the enemies are spawned, the player is spawned, and then eventually the score with its lives actually comes along too. So if I do another proper test just to see what the original SEUCK does with this data, then the top left enemy should be completely static and the top right enemy should move, right? So the enemy spawns, it waits for a few frames, and then even though I tapped left on the joystick, it's actually moving across 4 frames. I just counted that. And I think the other enemy as well, its movement was synchronized with 4 frames. So it's really interesting to note for debugging purposes that the enemies stay static for 4 frames before moving, which is really quite odd, isn't it? And we can see that the bottom right enemy also moves 4 frames upwards. So even though I tapped the keyboard joystick rather, only very momentarily, it's actually encoded 4 frames worth of movement. I didn't quite hit pause at the right point there, and again, pause is not working in the emulator. I think that's probably because a key got stuck down. There we go. Okay, let's try and do that. Catch that one more time. Let's make sure the Alt key is not stuck down. There we go. Now I've got it advancing 1 frame at a time. So the bottom left enemy now, which should be going right and then down, goes right for 4 frames, and then it goes down for 4 frames. It's a bit weird that the score and the player information only starts to get displayed on the screen after about 8 or 9 or 10 frames. It's almost as if the score update for the sprites is not executing every single frame. That might be the reason why, to be honest. Interesting. So let's save that as test movement, or test moves 1. And let's do a binary comparison. This is the standard workflow that has been basically used in all of the previous videos. Edit stuff in the editor, save incremental data changes, and then look at them in the file difference viewer. Beyond compare, which is a great tool, very useful. In the SEUCK editor as well, actually, just checking something, the enemy had the original speed of 1. It was moving quite slowly. If I change the enemy's speed to be 3, we can see actually they move a lot further. So they're still moving 4 frames, but they're moving 3 times further each frame. You see there, the enemy has moved a couple of characters at least from the top right hand corner. And if I change the speed back to 1, the enemy moves a lot slower, even though it moves the same number of frames. But it doesn't move as far. So this is important to note, is that the movement that's encoded in the memory is independent of the movement speed of the enemy. So the movement data encoded in the memory is basically move up, down, left or right, or diagonals, for numbers of frames, as opposed to move with the velocity. It's basically saying move up, down, left or right, but it's using the velocity from the enemy bits. We haven't looked at the enemy bits yet and how they are encoded in the memory, but we will in the next video after this one, I expect. Because the enemy bits describe what the score is and the speed of the enemy, but also what happens with the enemy fire rate, what it fires, what it explodes as, for example, the sound effects, what happens when it collides with the player, so on and so forth. From the previous video, we already pretty much know where the enemy data is going to be encoded in memory. I mean, we can see here, this is the start of the enemy attack waves data, and we already know that this is the encoding used for where what enemy animation type is to be spawned, where it gets spawned in the map, where it gets spawned on the screen, and also it has 2 bytes for an address of what we think is movement data, and I'm pretty sure it's movement data, obviously. We can see here immediately that the first enemy has CB as the address, and then the next enemy has C9, and the next enemy has C6, and the next enemy has C3 as the low byte of the address for the attack wave's data. This tells us that the 4 enemies that were added use descending memory, so the first movement data for the first enemy is quite high up in memory. The next enemy attack wave data is underneath it, it's lower in memory, and then the next enemy along is lower in memory still. So the movement data grows down from the top of memory backwards, basically. These are the bytes for the test movement data. So these bytes here go all the way up until, so it's not including those 2 bytes, because those 2 bytes are the memory address. Don't forget, with the previous video showed that there are 2 memory addresses being used. So this is the raw movement data that has been saved at the top of the attack wave's memory block, right at the end. And we know that we've got 4 enemy attack waves encoded because I can see that we've got 4 FF characters there. FF looks like it's the end of the attack wave movement data. Each enemy points to the start of the attack wave movement data, but the movement data goes backwards through memory, so we know pretty much that the top left static enemy uses those 2 bytes. The top right 4 frames of moving left data use those bytes. The bottom right 4 frames moving up enemy uses those bytes. And then the last enemy that was added has 2 movement steps, don't forget. What was it? Moving right and then moving down. So it actually has an extra byte. We know this because when we have a look at the raw placement data, which is the block of memory growing from the beginning of the attack wave's memory block that was previously reverse engineered in the previous video, we know that these are the memory addresses. So we know that CB3F, which is actually 3FCB because it's low byte, high byte format, the least significant byte comes first. We know that 3FCB, for that first enemy, points to this byte here. We know that the next enemy that was added points to that byte. We know that the next enemy points to that byte, and we know that the next enemy points to that byte there. It's quite intriguing that every single enemy starts with the same byte, even though the movement data, even though the movement goes off in different directions. Just to clarify, I'm going to say that that's enemy 0, that's enemy 1, that's enemy 2, and that's enemy 3 with those pointers, okay? So the movement, attack wave's movement data gets processed backwards until I think it hits that FF value there, and I think FF is a good end of sequence byte value. So we need to understand how these bytes are obviously working. Now, it's interesting to note that the enemy that adds 1 extra step of movement, the bottom left enemy, which does 4 frames right and then 4 frames down, even though it adds an extra movement step, it only adds 1 extra byte. So we can say, for example, that the movement is encoded into 1 byte for each change in direction, for example. The static one, which has no movement at all, only uses 1 byte, which is that 10 byte, which is present in every single enemy. And every enemy, when it spawns on the screen, is static for 4 frames. So let's start writing out some initial hypotheses here, that the low nibble means movement, and that the high nibble is the step count, for example. I think we need a little bit more data to really make sure of this. So the movement that was used so far only moves up, down, left and right. So let's try adding some extra enemies that have diagonal movement, just to really try and understand the data a little bit better. So let's insert another enemy of the same type as before in the same map position. So there are the other enemies. Let's put this enemy in the middle and then move it down right, up left, and then down left. Let's save that as test moves 2. Let's make the notes as we go along so we don't forget. After saving, let's test the game in the editor. We'll step the frames one by one so we can actually see what's going on. Okay, so there we go. There's the enemy in the middle, down to the right, up to the right, up to the left, and then down to the left. 4 frames each. Kind of expected, really. So let's write down what we have in the debugging text file. The movements that we will expect to see. There we go. And then let's have a look at the binary bytes difference between those 2 files. So that's the placement data, and then we have the extra bytes for the extra movement that we are expecting there. So we're looking to copy these bytes. Just there we go. That's the new data that was added. So we'll put those there. Now we can pretty much ignore this first byte because at the moment it's static. It's unchanging for every single enemy that we've added. But we can see here, look, this value 5 is interesting because it has 2 bits. So it looks like we have a bit pattern in the low nibble. So for example, 2 equals left and 8 equals up. And looking at the data, we've got 4 equals left. We've got 1 equals right. Sorry, 4 equals down. Let's arrange these in ascending order, okay, numerical order, and write out the bit pattern for each of these values. So let's put the bit pattern there. By convention, of course, the least significant bit, the smallest bit, is to the right, and the most significant bit is to the left, like, you know, writing in decimal, right? The least significant decimal number is to the right. Units, tens, hundreds, thousands goes from right to left. But this value 5 is interesting because it means that we have down and right bits enabled, which is correct because the enemy moves down and to the right first. And then the next step along is, well, the value is 9, which means that we have 8 and 1 enabled, which is up and to the right, which is, again, correct according to the sequence of moves that we want the enemy, that we programmed the enemy to move in, right? So yes, definitely the low nibble is movement data. But we need to understand the high nibble. I mean, we can assume that it's a step count, but we need to test this hypothesis, right? It makes sense, it's a step count. So let's load the previous data, the test moves 2 data, rather. But this time let's add an enemy which has a much longer movement sequence. So we'll move a long-ish distance to the right, we'll move a short distance up, a short distance left, and then a longer distance down. So we'll save that as test moves 3. Let's just write down what we're doing in that file so that we don't forget. So it was a long right followed by a short up and short left. and then a longer down. So when we have a look at the binary difference now, for the movement data, for that new file that was saved out, we're going to see these differences. That's the new enemy attack wave placement data. This is the new movement data, again added towards the end of memory of the attack waves data, memory data block. And we can see here that the high nibble, look, we've got values f in there this time instead of 1. So I think from this we can conclude that f is a long value, many steps, and it seems to be repeating the same movement direction 1, which is to the right, but it repeats it for 2 times f steps. And then there is a short movement up and a short movement to the left, and up is 1 step shorter than left, and then the final movement is a longer movement in direction 4, which is down. So we have enough data to reproduce the behavior in code now from what we're seeing with the original SEUCK. In the game update loop, we have animation trigger enemies. Now, animation trigger enemies was taking the placement data from the attack waves data, and it was reading this structure. And part of how the structure is read is that it's reading the 2 bytes for the animation movement data, or the attack waves movement data, which comes from bytes 2 and 3 in the placement structure. And this data, because it uses the original SEUCK data, is using the original SEUCK memory offsets. So those memory offsets for the movement data address need to get modified, which is what this little piece of code here does, is that it just basically adds on the difference between where the SEUCK memory thinks it is and where actually the memory has been included in the new code. So we need to adjust the memory. Now this could have been done during the assembly, during the data import, but I didn't bother. I just added a quick little address manipulation here inside the 6502 code, so it does the address relocation at runtime rather than at assembly. So then the next part of the game update loop is that it processes the animation movement and the frame updates. So the previous videos handled the sequence of the animation and how it looks and how it animates and updates on the screen, but this time the process enemy movement, when it runs, it takes a look at the animation movement frame count and the animation movement move bytes which are associated with each enemy, and it figures out how to step or how to move the coordinates for the enemy according to the movement byte which is currently being processed. Because the trigger enemies routine, once it finds a free slot for the enemy to trigger the enemy into, or to spawn the enemy into in the animation routine, what it does is that it initializes the movement data, memory address pointer, and it also sets the animation movement frame count to 0, which is like a trigger to tell the animation routine to read in the next movement byte. Okay, the animation trigger enemies always runs before the animation update frame movement routine, so that when new enemies are spawned, they will get this little update flag to basically say start reading in new movement data. Okay, so that's why the animation movement frame count is there, but the current direction of movement is in the animation movement move byte, which is a byte which is associated with every single animation that's visible on the screen. Of course, the player, even though it has the memory allocated for this, it doesn't use it because the player is not an enemy. However, the frame movement move byte is this byte, or these bytes, which are encoded inside the movement data from the attack waves data. So If that's FF, it basically stops the enemy from moving any further. But and then it looks at the count, and if the count is not equal to 0, then it keeps on moving in the direction that the movement data says. Otherwise, if it starts off as 0, then it basically reads in the updated movement byte from that movement data, and then it uses that current movement byte from the movement data to then process the actual the directional animation, but it also processes the move steps. So we get to this code here which looks at the input direction for each animation, and it looks at the animation directional bits, and then the for the player and also for the enemies and also for the bullets as well, the direction, because the direction is encoded in the animation system automatically chooses whether or not it displays a sequence or whether or not it displays the directional animation. Because don't forget that SEUCK has the concept of sequential movement, or sequential sequences for the animation, or directional movement, where you have up to two frames for each direction that's being shown. And then once it processes each byte for the movement, of course it has to move backwards through memory, which is what this update the pointer for the next command does. Now, when the enemy is actually processing the movement bytes, then of course it needs to update the coordinates for the memory, for each enemy in memory. So each enemy has X and Y coordinates, and those are X and Y coordinates that are used for the sprites on the screen. And the sprites in turn are the values. Sprite coordinates are those coordinates used for the multiplexer. So looking at each bit, it basically pulls out each bit, and if it's up, down, left or right, it uses the accompanying coordinate update logic. And this allows the movement bits to also represent diagonal movement. So if we take the last debugging data that was just saved out, the test moves 3 file, and then we include that in the code and then run with it, what we expect to see is that we expect to see all of these test enemies moving around according to the movement that we put into the SEUCK editor. So this is new. This is the new code now running on the right. By convention, the new code is running on the right. I've paused it there with frame 673 that you can see there on the top of the title bar of the window. I'm advancing each frame's movement now, so you can count the frames. They move for 4 frames. I'm single stepping each frame to make it easier to count 1, 2, 3, 4. There we go. The next 1, 2, 3, 4, and so on and so forth. So this last enemy, if you remember when we added it, it moves longer to the right, shorter up, shorter left, and then longer to downwards. So that's what we see. I'm moving the player around with the joystick. The player is in light blue there. And if I press the restore key, it restarts the game. And now I'm pausing it. The first frame comes along, renders the map. Second frame comes along. Third frame, enemies are spawned. Can count the frames for the movement, and everything looks great. Right? The movement that's in this test from this test moves file appears to be the same as the movement that is visible in SEUCK. Let's get SEUCK so SEUCK will be on the left, the original SEUCK will be on the left, and the new code will be on the right. So let's load it. Let's load test moves 3 in SEUCK. Let's do a proper test with the SEUCK game on the left. So SEUCK is on the left, and then I'll run the new code on the right. So let's run SEUCK on the left, press the start on the left, and then reset by pressing restore on the right hand screen. We can see that they're practically in sync, right? The movement looks identical. The placement of the enemies. Now, my improved code actually renders a couple of extra scan lines above, and a couple of extra scan lines below SEUCK, so we're seeing a little bit of extra screen data. Well, actually the screen is shifted a little bit, but that's okay. But what we're seeing here is that the sprite positions as they end up are basically exact as far as we can tell with regards to the pixel positions, with how the game looks. So that, I think, is the movement data reverse engineered and documented. So let's copy the pertinent pieces of information, the relevant pieces of information from the debugging text file, and we'll put that in the document for ease of reference next time. So there we go, nicely formatted in the document. I think next video we'll look at the enemy firing score, speed, for example, and all of that other associated enemy bits data. What we can do now is that we can enable the game demo 1 data that was exported before, and we can try that in the new code on the right, and then on the left we'll run game demo 1 in SEUCK, and we can see that the enemies when they spawn, they look correct, and we'll compare it with the original SEUCK game demo 1 on the left. So let's sync up the views as best as possible. Here we go. So we'll start the game on the left and then reset the game on the right. Not quite synced, but it'll do. So yeah, we can see pretty much that the enemies look like they're following their correct attack waves. They look in sync for what we expect to see. The enemy bits describe how often the enemies should fire, for example, so that's why we're not getting any enemy fire in this demo. But the rest of the sprites, they look like they're in the correct position, right? So all of that looks great. And when we get to this part, the boss sprite should come along, and the boss sprite has a concept of linked enemies. So the other linked enemies are just basically reusing the movement data. Now, SEUCK on the left is slowing down and flickering a bit. The new code on the right is faster and not flickering, and there's no slowdown. So that's why the code on the right has progressed in its scroll compared to the left-hand one. So SEUCK on the left was counting frames, as I do. I count frames too, but frames weren't slowing down in my code, but they were slowing down in SEUCK. So let's get them synchronized up again between the left and right, and all of the other enemy attack waves, they look identical, right? Apart from the new code on the right doesn't have shooting or anything like that going on. One of the advantages, of course, of having code is that we can add extra functionality. So in this example, I'm going to be enabling the enemy AI test block of code. This means that when the game encounters enemy type or animation type number, 24, and when it finishes the pre-programmed movement for that enemy, instead of just standing still, it will run extra code which chooses random directions to run in, and from a table, and using a random routine and also a table for random direction table there, the safe random direction tab routine. And the rand routine, it basically picks a random direction to go off and run for how many number of frames, for a random number of frames I think it was. And this uses enemy test data. So this uses, like it says in the description, it uses the third demo game, but it modifies the map to provide an area for the enemies to run into at the beginning of the game, and then it allows the enemies to run around freely inside it. So in the original version of SEUCK, of course, there is no in inverted commas, enemy AI code. So the original version of SEUCK, once I load that enemy test AI file, which is there, once I load that file, you'll see what I mean. So object animation type 24 is this enemy, which is the humanoid or whatever it is wearing a brown clothes or jumpsuit or whatever it is. The game, if I give it a proper test, you'll see that the enemies run in at the beginning, and there are two static enemies there already. A third one runs into this microchip, if you like, fenced off area. If I run that same example with the new code, the two static enemies have started running around. The third enemy runs into the fenced off area, and then once it reaches the end of its movement, it also starts running around in random directions. There you go, see? So this allows SEUCK games, for example, to be expanded with enemy AI, in inverted commas, movement, which is something that you would be, it would be quite hard to put that kind of enemy AI movement into the real SEUCK, because you'd have to understand how all of that code works and then inject the correct logic. Because we've got the source code in the new code, because the source code is all available, it's very easy to modify and add extra functionality like that. So you can see here that the level progresses to include the previous levels from the demo game number 3 example. But you can see on the left it's flickering quite significantly. On the right with the new code, of course, there's a lot less slowdown. So I think we'll leave this video there. Thank you very much for watching these Commodore 64 retro games reverse engineering videos. If you like this kind of content, then please do consider liking or subscribing to this channel. And if you really like it, please send me a super thanks. It's all very well appreciated. Thank you very much for watching. Take care. Have a great day wherever you are.